Mr. Chernetzky, and this is your Unit 2 review. So we'll go through our review and how we get the answers for each one. So, question number 1. The heights of American men aged 18 to 24 are approximately normally distributed with a mean of 68 inches and a standard deviation of 2.5 inches. Only about 5% of young men have heights outside the range. So, which of these matches that distribution? So, to illustrate what's going on here, let's go to our, you look at the front of your packet or really pull up any normal curve here and recall our 68, 95, 99.7 rule here. So if we are normally distributed with a mean of 68 and a standard deviation of 2.5. So let's see if we can plot that. So normal 68, standard deviation 2.5. That means our median, or sorry, our mean is 68. And then every standard deviation away. So this would be 70.5, one standard deviation away. This would be 73. And this would be 75.5, 3 standard deviations away. And then on the other side, we'll just subtract 2.5. So this would be 65.5. This would be 63. This would be 60.5 inches. Okay. So again, the question was 5%. So that means that outside of that range would be 5%. That means that inside that range would be 95%. So at 95%, that's within 2 standard deviations. So that's between 63 and 73 inches. Or answer B. Okay. On the previous information, what percentage of men are over 70.5 inches tall? So let's go back to over 70. Let's take, yeah, 70.5. Okay. So really, what is shading beyond that first standard deviation? Okay. Well, there's several ways to do this. I think I'm going to go the approach of looking at the shading on the other side. And I know that right from the middle, from the mean, all of this in red, that's 50%. And then half of that first standard deviation, half of that 68, right here, which I'll shade in orange, that's 34%. So 50 plus 34% equals 84%, and that's left of what I'm talking of the shading that we were looking at. We want this shading, so really our answer would be 100 minus 84%, which is 16%, which is right here. Answer C. Okay. For number 3, for the density curve shown to the right, which statement is true? So the biggest thing to remember with density curves. Oops. The area under this curve is always 1, meaning that 100% of our data is contained underneath this curve. Okay, so right off the bat, I know that A has got to be the true correct answer. but we can eliminate the other ones too just by looking at our graph. Density curve is symmetric. Obviously, it's not symmetric. Density curve is skewed right. No, it's skewed left. So not C. And it's definitely not normal. Normal has that nice shape that we saw in the previous problem. And it's not E because we already indicated that A is the correct answer. Okay. All right, for 4, for the density curve shown above, which statement is true? The mean and the median are equal. No. This is a left skewed density curve. So that means that our mean is going to be less than our median because there's probably some sort of outlier, or just our data to the left here is going to be pulling on our mean. Our mean is getting pulled towards that tail away from our median, so it's going to be less. Okay. All right. The area under the standard normal curve corresponding to negative 0.3 z-score to a 1.6 z-score. Okay. Well, if we draw our normal curve, normal standardized curve, mean centered at 0, standard deviation of 1. What we're talking about is from about here, negative 0.3 to positive 1.6. So shading in this area. Okay. How can I look that up? Well, there's two ways. I could use my calculator, or I could look up in the table A. So in our calculator, so let's go to second distribution, and we're going to go to normal CDF because we have z-scores, we're trying to find an area. Let's clear that out. So our lower bound is from negative 0.3. Our upper bound is positive 1.6. Mean of 0, standard deviation of 1. Okay. There's our output. And we see that that area is about 56.3%, which corresponds to answer C. Okay. Number 6. The graph at the right is a norm probability plot for the amount of rainfall obtained from 26 randomly selected clouds. Which of the following statements about the shape of the rainfall distribution is true? Okay. It is not approximately normal. If it was normal, we would expect our normal probability plot to be a straight line. It is not. Okay, so it's not normal. It's not approximately normal. And now we have to, it definitely has outliers because that's what's causing it to be not normal. There's definitely some outliers here and here that are way off our projected normal plot. So the question is this a skewed left or skewed right? Well, our outliers appear to be on the right side of our graph. These are the points that seem to be causing the most problems. So I would definitely say that this is a skewed right problem. Okay. Number 7, the distribution of time it takes for different people to solve a certain crossword puzzle is strongly skewed to the right, with a mean of 30 minutes and a standard deviation of 15 minutes. The distribution of z-scores, so I mean if we took all of those scores, divided them by or subtracted them from the mean and then divide them by the standard deviation. Okay. Well, the shape is not going to change. Okay, each point is going to be moving the same way. So if we start it out skewed to the right, we're still going to be skewed to the right. The question is, what happens to our mean or standard deviation? Well, if we subtract everything by the mean, well, every point by the mean, then that means our mean is going to go to 0. And then if we divide every point by the standard deviation, our standard deviation is going to go to 1. So we're going to be skewed to the right with a mean and standard deviation of 1. Question 8. Cumulative relative frequency graph shows the distribution of lengths in centimeters of fingerlings at a fish hatchery. The interquartile range for this distribution is approximately, well, so remember IQR is Q3 minus Q1. It is not two values, it is one value. Okay, so right off the bat, I can cross off A, B, and C, because an IQR is not two things. It is a range. It is one value. Well, how do we figure out what Q3 and Q1 are? Well, first quartile is at the 25th percentile, so somewhere around here is Q1. So go, where does that hit our graph? I don't know, somewhere right about here, maybe 5.3-ish, guesstimating. And then where is Q3? Q3 is somewhere about here at 0.75 or 75th percentile. So we'll mark here and see where does that hit our graph. Somewhere right about there. So Q3 is somewhere about 6.5. So estimating 6.5 minus 5.3 is about 1.2. So you should have something like 1.2 or something close to 1.2. Definitely not 2. Okay. Which of the following properties is true for all normal density curves? Okay. First of all, I can definitely say that they are all symmetric. So number 1 is correct. The curve reaches its peak at the mean. That is definitely true for a normal density curve. And number 3 sounds good. 95% of the area under the curve is within 1 standard deviation of the mean, except, well, here's the problem. It's not 1 standard deviation. It would be 2 standard deviations is where 95% of our area is set. So question 9, only 1 and 2 are correct. Okay. Number 10. A fire department in rural county reports that its response time to fires is approximately normally distributed with a mean of 22 minutes and a standard deviation of 11.9 minutes. Okay, so right here is 22 minutes, and we want to know what percent is over 30 minutes. So somewhere here, 30 minutes, a little less than 1 standard deviation away. Okay. So first thing I want to do is I want to figure out what is the z-score for that. So z equals your score minus your mean divided by standard deviation. So 30 minus 22 divided by 11.9. Yes. So there's our z-score, 0.672. Okay. I go back to my, well, if I then convert that to a standardized normal curve. Same shape. I'm just trying to find the area at 0.672 standard deviations away. So we'll go to our calculator. Hit second vars, go to normal CDF. Our lower bound was at 0. Was it 672? Our upper bound is essentially infinity, so I'm going to do 1, hit second, E99, that is a really big number. Mean of 0, standard deviation of 1. Okay, so approximately 25%, which is answer C. The other way that we could have looked up values, we could have gone to table A and looked at a z-score of 0.672. So if we look at z-score 0.672, so here's 0.6, 0.6, and then 0.67 is right here, and we're getting about 0.75, okay, somewhere around there. So it seems like the opposite of that. And the reason we're getting that 0.75 is because our graph shades from left to right. So this is really what we're finding over here is this 0.7486, which if we subtract from 1, we're going to get that 0.2514, I think. Okay. And that would be the answer that we're actually looking for over here, this shaded area. Okay. That's the end of our multiple choice. Let's take a look at some free response. Number 11, Dow Jones Industrial Average Index is measuring stock performance of 30 large companies, often used as a measure of overall economic growth in the United States. Below is a computer output describing the daily percentage changes of the Dow for the first 3 months of 2009 and 2010. Okay. A negative value indicates a percentage decrease in the index for that day. So, consider a day when the Dow increased by 1%. In which year, 2009 or 2010, would such a day be considered a better day for the stock market relative to the other days? So, it's saying in which year, 2001, 2010, is a 1% better. Okay, not like raw like score, like how much better in the economy, but relative to that particular year. So in order to compare that, we're going to compare both of those normal distribution. So over here, we'll draw a normal distribution for 2009. And that had a normal distribution with a mean of negative 0.198. Means on average, you're decreasing throughout the year. And a standard deviation of 2.331. Okay, so right here in the middle is negative 0.198. Then in 2010, I'll do a different color. Good. Here's 2010. The mean is 0.078 and the standard deviation is 0.821. So right down the middle, 0.078. That's the mean for 2010. So we're asking, when would a 1% So a value of 1 on our graph be the best areas. So in 2009, that would be over here. Yeah, something like that. So there's 1. Actually, we don't need a shade. We're just trying to figure out which is better. Oopsies. Okay, that's all right. And then over here, this is also where 1 would be. So they look similar in our graphs. It's hard to tell which value is higher relative to its year. So what we need to do is we need to calculate z-scores for both of those. So for 2009, the z-score would be 1 minus the mean, so minus 0.198 divided by 2.331, which if we punch that into our calculator, we get a z-score of 0.5139. And then for 2010, same thing. 1 minus 0.078 divided by 0.821. And that gives us a z-score of 1.125. So, which one was it better? In 2010, that is over 1 standard deviation better than the mean than in 2009, which was only a half a standard deviation away from the mean. So that was a better year to have a 1% to be having an increase of 1%. Okay. Assuming the distribution for 2009 is approximately normal, estimate how many of the 61 days in 2009 decreased more than 1%. So we're in 2009. There's our normal distribution. 0.198. Standard deviation 2.331. And here's where we're trying to figure out the shading greater than 1. Nice thing is we already have our oh, I did that backwards. Nope. I needed it. I'm not looking for more, we're looking for decrease. Sorry. Read that wrong. So that would be -1 actually over here, and we're looking for this shading. So we are going to have to calculate the z-score. So -1 minus -0.198 divided by 2.331, and we get a z-score of -0.344. Okay. Well, how do I use that z-score to calculate how many days? Well, I can get a percent. Figure what that percentage is. Now we have a normal, standard normal distribution. So at 0, our z-score, same spot, 0.344. And we can look this up on our calculator or in our table. So if we're looking at in our calculator, we would go second vars, normal CDF. Our lower bound is negative infinity, so -1 E99. Oops, 2 nines there. Okay. Our upper bound is our z-score of -0.344. And we'll go ahead and paste that. And we see about 0.365 or 36.5% of the days. So I'll make sure I illustrate, oops, where I got this data. So normal CDF -1 E99 to -0.344. 1. Okay, that told me 0.365 or 36.5% of those days. How many days is that? Well, the last step would just be what is 36.5% of 61 days? So we would just do that number times 61 days, and that's 22.29 or 22.3 days. Okay. Estimate the 19th percentile of daily change for the first 3 months in 2010. Okay, so in 2010, here's our normal curve. Point 0.078 for the mean, 0.821 standard deviation. Okay. I am looking for the 19th percentile, so that is somewhere over here. I'm looking for that value. So I need a z-score that will match that. And if I use my calculator, since I'm looking for a percentile, a z-score that go with that percentile, rather than plugging in a z-score, we're going to go to second distribution, and we're going to do inverse norm. Since I have a percentile, so my area is going to be 0.19. Okay. If you don't have this tail in your calculator, it defaults to left, which is fine. That's what we're looking for anyway. So if it was like the upper top 19%, you could switch this to a right, or you could take your answer and or you could take your area and just subtract it from 1. Okay. So there's our z-score that indicates a 19th percentile, so -0.877 or -0.878 if we round. And now I'm going to take that z-score and figure out what would that be in terms of an actual percentile, or not percentile, an actual percent in our calculations. Oops. So that's going to equal the score minus the mean, which is 0.078, divided by standard deviation. And if we backwards solve for that, multiplying by 0.821 and then adding that 0.078, we get negative 0.644 or 64.4 decrease. Okay. Number 12. Normal body temperature varies by time of day. Series of readings were taken of body temperature of subject. Mean reading was found to be 36.5 degrees Celsius with standard deviation of 0.3. If you want to convert temperatures to the Fahrenheit scale, here's the formula. So you're going to multiply the scores by 1.8 and then add 32. So what happens to our mean? Our mean is going to be multiplied by 1.8 and added 32. So mean is just going to be converted. So 36.5 times 1.8 plus 32, which gives us 97.7 degrees Fahrenheit for the new mean. Okay. Standard deviation. The only thing that affects the standard deviation is the multiplication part. So just the 1.8. When we add 32, all that happens to all of our numbers is that it shifts by 32 degrees. But the spread does not change by adding. So that has no effect on the standard deviation. Only the multiplication does. So the standard deviation is going to be 0.3 times 1.8, which gives us a standard deviation of 0.54 degrees Fahrenheit. Okay. Number 13. Local post office weighs outgoing mail and finds that the weights of the first class letter is approximately normal, mean of 0.69 ounces, standard deviation of 0.16 ounces. So let's graph our normal distribution. There's our normal distribution, 0.69 mean, standard deviation of 0.16 ounces. Okay. What is the 60th percentile? So that's over here. So we need to figure out what is that value. So we're going to do inverse norm. And we're going to do 0.6. And that gives us a z-score of 0.25. Okay. So then I need to convert that into actual weights. So plug that into our z-score formula. So that's